So, curiosity killed the cat, huh? Maybe he was too curious about fire. So when I was in the Boy Scouts, I learned how to build a campfire. And one of the things about that really stuck with me, that we were taught, is that fire needs three things: fuel, heat, and air. Now, in reality, the air is just a source of oxygen, but otherwise that pretty much sums up all forms of traditional combustion. That's why I like it so much. It always works. If I ever have problems with a fire I'm building, I go back to that triangle of needs. Now, fuel is the most visually obvious need to most people who have ever looked at a campfire, and it's a huge subject on its own. A large fraction of everything in existence can be made to undergo some form of combustion with appropriate heat and oxygen. The sheer number of possible fuels makes it a massive topic. There's pros and cons and different properties for all these fuels, but at its most basic, just about everyone understands that you need to have something to burn if you want to burn something. The second thing fire needs: heat. It's actually pretty tricky to supply to a fire that hasn't started yet. You'll know what I mean if you've ever tried to do it without some kind of modern convenience like matches or a fire steel, like a sparking steel. These mostly consist of some kind of fuel that burns with very little heat, and you can just ignite with friction from the force you put into it. Normal kitchen matches, and like the matches that you would find in a book from a restaurant, say, they're actually only half of the fuel in the match head. The other half, part of the pair of chemicals that forms the fuel, is actually in the striker. And so when you put them together and then add the friction for that heat, that fuel has enough energy to light. It's very volatile, which is why they keep it separate. And like a lighter you might use, it uses butane fuel, but then that itself is ignited by a burning spark from a sparking steel that is built into the lighter. And they usually call it a flint, even though it's not. But once a fire started, it makes its own heat. Once your main fuel is burning, you shouldn't need an outside heat source. And that leaves oxygen. Now, this is the interesting part. Fire is a chemical reaction. Oxygen is actually being reacted with the fuel. And so the more fuel you're burning, the more oxygen you need in a fixed ratio. So the structural bones of wood that you might burn in a campfire are basically made up of cellulose. And lignin is basically the connective tissue. Cellulose is a long chain of tightly bound sugars, while lignin is more a complicated sort of plant plastic that's made up of a different blend of herbs and spices, depending on the kind of wood. But in the end, they're basically made up of hydrogen, carbon, and some oxygen. On the subject of fuels, things made of hydrogen and carbon, hydrocarbons, make up all the petroleum-based fuels we use, and they're mostly just dead plants. So what's the point? Well, when you react hydrogen and carbon and maybe some oxygen with more oxygen in a fire, what do you get? Well, it depends how much oxygen you've got to go around. In ideal combustion of wood or a hydrocarbon fuel, the hydrogen combines with oxygen to make water, and the carbon combines with oxygen to make carbon dioxide. And most controlled combustion reactions, like a gas stove or a car engine, are designed to work this way. But if you have limited oxygen available to any single molecule of fuel that you're reacting, you can get carbon monoxide if there's not as much oxygen, or if you have even less, you'll form soot. The part of soot you see is loose carbon that didn't have any oxygen to pair up with. And in reality, when you get into that situation, there's no balanced equation that forms carbon and still forms water. If there's a shortage of oxygen to allow complete combustion, then there's also not enough oxygen to form water with the hydrogen in the fuel. So in addition to the carbon you also get a lot of fuel that isn't all the way burnt. It's not all the way reacted. So there's still hydrocarbons. They're referred to as polycyclic aromatic hydrocarbons. They're smaller than what's in the fuel, but they've kind of been released as individual molecules that are usually smaller than what the fuel started as. And polycyclic aromatic hydrocarbons are also known as PAHs, because that's a lot of crap to say. They're also known as a big pile of toxic and carcinogenic chemicals, and one of the main reasons that catalytic converters exist for your engine. Now, gasoline, like in a car engine, only burns in a narrow range of ratios with air because of the amount of oxygen required. This is why modern cars atomize the fuel so it can effectively mix with the air before it burns. While exposed gasoline will vaporize and mix with air naturally until it reaches a ratio that can ignite, liquid gasoline settles in a container because of gravity, and it can't effectively mix with the air to supply oxygen for combustion, and so it'll only burn right on the surface of the liquid where it evaporates and mixes with the air. Now, I know you've seen this in action because we've gone backpacking together. Our backpacking stove burns gasoline, and it doesn't have a fancy fuel injector that atomizes the liquid fuel. Instead, the jet sprays out a mist of liquid fuel from the pressurized fuel bottle unless the stove has been primed. So when you prime the stove, you burn a small amount of liquid gasoline in a cup under the main burner, and that heats up the stove. The stove is designed so that the last bit of fuel pipe before it gets to the burner is a thin, solid metal pipe that circles up right next to the flame before it feeds the little spray jet for the fuel. So when the stove is hot, the fuel goes through this loop, heats up, and evaporates in the pipe before it gets out the jet, where it'll then spray up into the main burner and mix with air when it leaves that jet, instead of just kind of pooling as a liquid. So when you prime the stove, the fuel burns as that liquid. You ignite the vapor that's naturally evaporating off of the pool of liquid with a match, and then the flame continually burns the vapor as it comes off that pool of liquid, just when it's mixed with the minimum amount of oxygen it needs to burn it all, which means you get an oxygen low flame that's yellow and nasty and smoky and sooty. So once it's heated, and a stove like ours or many camping stoves is burning fuel as a gas, especially when the fuel is supplied at the higher end of its pressure range, like when you've just pumped up the gas canister, or if you use a brand new pressurized fuel canister of like butane, the gas is mixing very effectively with the oxygen, and the flame gets a really kind of deep blue flame color, and it'll actually make a kind of whooshing or hissing or roaring noise, and that's usually indicative of a flame that has more than enough oxygen. I'm not sure, but I think this might actually be especially bad on our stove because it was designed to be used at high altitude where the air is thinner, so there would be less oxygen. So people who are most familiar with this kind of oxygen and how it affects flames would be people who use oxygen gas torches. So the gas reference here would be a fuel gas, and oxygen would be separate. So by supplying the pure oxygen gas in addition to fuel, it can be burned at higher temperatures by ensuring it gets exactly as much oxygen as it needs. So a lot of high temperature welding before we used a lot of electric arc welding had to be done this way with an oxygen supply, and cutting metals can still be done this way, and many people still use Oxygas torches for welding. But on this type of torch setup, you've got two separate gas supplies, one for oxygen, one for the fuel, so you have two separate control valves. You can adjust the fuel flow as well as the oxygen ratio. So people who use these kind of torches, these Oxygas torches, will refer to the flame produced based on how much oxygen is being supplied. A flame with just the right ratio for combustion is called neutral and is a clear blue color, and that's what you want if you're just heating stuff up with no real special needs. A flame with an excess of oxygen supplied is called an oxidizing flame. The flame will get shorter and darker and will make that roaring noise like our backpacking stove. Usually welders will avoid this because it'll actually introduce oxygen into the metal's surface, consuming some of the elemental metal and forming metal oxides that are often brittle. Now, a flame that is produced by these torches that is low in oxygen will tend to be more yellow and called a reducing flame because it will actually reduce the oxygen present in the materials it's applied to by using it to combust the fuel gas. It's also called a carburizing flame because when you apply it to metals, it'll tend to introduce carbon into the molten metal, carbon that would be forming soot otherwise, like the flame from priming our stove or burning liquid gasoline in any other situation. You might burn a pool of liquid gasoline. But my favorite thing about Oxygas torches is how they're used for cutting steel. So they're a little different in design this way. They have a special third supply tube that also supplies a secondary oxygen input that can be toggled with a little trigger. And this secondary oxygen stream flows through the center of the torch head. And the other gas flows are arranged around the outside on the perimeter. And it's designed this way because the gas used for fuel when welding is not actually the primary fuel combusting when you cut steel. The iron in the steel is the primary fuel. So the first oxygen flow, the primary oxygen and the fuel gas, are ignited and used to preheat the steel at the start of a cut, like when priming the backpacking stove. But once it's red hot, or specifically at the ignition temperature of the iron in the steel, that trigger is actuated, and the extra oxygen feed through the center of the torch, the oxygen blast, hits the heated metal, rounding out the triangle of fire here with the iron fuel, the heat provided by the fuel gas burning with oxygen, and then that oxygen blast providing extra oxygen to the iron that's now heated, and the iron combusts. But instead of forming water and CO2 like a hydrocarbon or wood, there's no hydrogen or not much carbon in the steel, but there's a lot of iron, and that is what's burning, and it forms iron oxide with the oxygen. Makes sense. Iron oxide, just like rust. And then that iron oxide melts at a much lower temperature than the steel. So once it forms, it's either forms as a liquid or turned instantly into a liquid and blown right out the back of the cut that you're making in the steel by the oxygen blast. So this reaction, just like more familiar forms of combustion, produces plenty of its own heat. So it proceeds much quicker once the initial preheat has happened and you turn on that oxygen blast, and it doesn't rely on the heat produced by burning the fuel gas around the edge of the torch anymore. I think that's super awesome. Also, like most metal oxides, any liquid iron oxide that lands on the metal while you're cutting is brittle when it's solid, so you can just kind of chip it off relatively easily once it cools down. So almost everything burns. Plenty of oxygen will probably keep a good fire going strong until you're out of fuel. And if that fuel releases lots of heat energy, even better. Welcome to rockets. Now, I'm not going to go into rockets now, really. I think I've talked for long enough. But I think it's pretty interesting how rockets use fuel and an oxygen source, just like an oxygas torch. And so rockets can use solid fuels that we don't normally think of as burning very well, in the same way that liquid gasoline doesn't burn very well just because it's a liquid and you need to wait for it to vaporize. It can't mix with the oxygen otherwise. So even if they're packed full of energy, we don't think of these solids as being particularly flammable. They tend to smolder or burn really smoky and slowly. So things like plastics and synthetic rubbers are actually some of the most commonly used fuels in hybrid rockets. And they're basically petroleum products, so they're packed full of energy. But because they're solid and dense, they just don't burn that well in the atmosphere. But when you supply that source of oxygen, they burn really well, and they can be used as a rocket fuel, particularly in hybrid rockets, like I said, which use a solid fuel and then a liquid oxidizer, so liquid oxygen, hydrogen peroxide, whatever. But a lot of people, including on YouTube, can actually use a gas that flows just like a liquid, and it's still a hybrid rocket. So you can hook up a gas oxygen source to a rocket nozzle that you construct and jam anything solid that burns in it pretty much, and the more energy dense the fuel, the better your rocket's going to be, the more thrust you're going to produce. But I've seen people making Salami rockets because there's some energy in there. That fat will definitely burn just like it's a hydrocarbon. So oxygen, it helps make stuff burn. And despite how hot it is, I think fire is pretty cool.